Now we're going to check for an example related with the flow work and the energy uh, concept that we have discussed in our previous video. Yeah, remember that at this point we're interested in measure the energy which is combining a flowing fluid. Yeah, a fluid which is passed through a pipe or maybe inside an engineering device. Yeah, here we have defined three main concepts: workflow related with the energy that we must supply to a fluid in order to get it in or getting out of a control volume. The specific energy of a fluid, yeah, which is related with the energy, the total energy that will have this fluid passing through our engineering device, and finally the rate of energy transport by mass, which is related with the quantity of energy that we supply or remove from our control volume because of the fluid flow. Yeah, when we enter or remove material from the control volume. So in this case, we're going to analyze the system. Here we have air flowing steadily through a pipe. Yeah, and the air has specific conditions: 300 kilopascal pressure and temperature of 77 Celsius degrees. Additionally, we know that this fluid is flowing with a velocity of 25 meters per second and a rate of 18 kilograms per minute. Yeah, in this case, we want to determine the diameter of the pipe, the rate of flowing energy, yeah, and the rate of energy transfer by mass. Yeah. So if you see, we need to recall for all the concepts or the theoretical concepts that we have defined in this second topic. So remember that at first it's important to state all the assumptions that we need to use in order to solve the problem in an in easy way. Yeah, remember assumptions that made us the problem really simple. So remember, this is not really an assumption; it's an statement in the problem is that we have a steady flow system. Yeah, yeah. We know that the conditions given in the statement are will be constant along the time. Um, in this case, we have air in moderate conditions. Yeah, uh, 300 kilopascal is 3 times the atmospheric pressure. So we can suppose that the ideal gas or the air behaves an ideal gas. Yeah. So if we have an ideal gas in terms of its energy, we can suppose that heat capacity of the air would be constant. Yeah. We suppose that a long time this heat capacity will not change. And finally, because we have a pipe in an horizontal position that is the most common, we can suppose that potential energy is negligible. Yeah, because we can center the reference system uh, for the fluid flowing uh, uh, in the center of the pipe. Yeah. So in this case, remember that velocity will be the the highest in the center. So in this case, potential energy would be very low. Yeah. Um, so here we need to recall too for the concepts and the definitions that we discussed in our previous topic. In this case, we start estimating the diameter of pipe. Yeah. In the second example of the previous topic, we deduce a formula which allows us to estimate the diameter of a pipe, yeah, when we have a fluid flowing through it. So remember, this diameter depends on the mass flow rate, the density, and the velocity. So I just have taken back this yeah, equation. Yeah. So if you see in the figure, we know the mass flow rate for the fluid, yeah, and we know the velocity. But here we don't have information about the density of the air. So, as we have supposed that air behaves as ideal gas, we can estimate the density from the ideal gas equation. Remember, the ideal gas equation states that the product of pressure times the specific volume equals the specific gas constant times the absolute temperature. Yeah, if we um, rewrite this equation in terms of the specific volume or the reciprocal specific volume, we can get this formula for the density. So in this case, we know the pressure and we know the temperature. So in the table A2 in Central Book, we can gain the value of the gas constant, the specific gas constant for air. Yeah, you have these tables in your Canvas LSM. So, uh, if you see here, we have used this value before 0.287. Yeah. So if you see in this case, it says that this quantity is in units of kilojoules per kilogram Kelvin. So remember that a kilojoule equals 1 kilopascal times per cubic meter. Sorry, really awful. Um, yeah. So 1 kilojoule equals 1 kilopascal times cubic meter. Yeah, this is the same. So I can write this constant in terms of as kilopascals per cubic meter divided by kilogram per Kelvin. So we substitute the value. Remember that this temperature must be absolute, so we need to convert Celsius degrees to Kelvin. Yeah. So the result, if I uh, haven't committed a mistake, is 2.985 kilograms per cubic meter. Yeah. So now we can use this density in order to estimate the diameter of the pipe. Yeah, we know all the information. We know that this is 4 times the mass flow rate, and obviously because we have different units for mass flow rate and velocity, we need to write both in the same unit system. So I have included here a conversion factor in order to write the mass flow rate in kilogram per second. So after that, we divide by the density that we just have estimated and the velocity of the air. Yeah. So the result of this is a diameter of 0.071 meters. Yeah. So this is such as um, a, this is near to 7 centimeters. Yeah. So this is a common pipe, I think. Yeah. So after that, we can continue with the energy calculations of the problem. At first, we want to estimate the rate of flow energy. So please be careful because we are looking for that rate. It means that we are considering a fluid energy, yeah, or an energy related with a fluid. So we have stated that let me show you, yeah, in this equation, we have stated the definition of the specific workflow. Yeah, it means the workflow for a flowing fluid per mass unit. Yeah, so this is not really a rate of flow energy. Yeah, this is a specific quantity. So this is the product of the pressure and the specific volume. Yeah. So in this case, we can write this equation in terms of pressure and density. Remember that specific volume is the reciprocal of density. So if we do the product of this quantity per the volumetric flow rate, we get a rate of flow energy or a, a rate of flow work. Yeah, it means the quantity of energy which we need to supply per unit time in order to uh, get in or get out the fluid across the pipe. So we just need to substitute this previous definition and do the product with the mass flow rate. Yeah, in this case, it's not required the unit conversion because I can state the rate in energy units per minute. So we substitute the mass flow rate, the pressure of the air, and the density that we have just estimated. So we get that the result of this is 1,809. Yeah, the result is 1,809 kilopascals uh, per cubic meter per minute. So remember that this quantity or this product, kilopascal times cubic meter equals kilopascal, kilojoules, sorry. So this quantity or the result of this is this quantity of kilojoules per minute. Yeah, so finally, we can estimate or we want to estimate the rate energy transfer. In this case, in our previous class or in our previous video, we have stated this equation for the rate of energy transfer by mass. Yeah, and depending on the mass flow rate, the specific enthalpy of the fluid, its velocity, and its position. So, at first, in the assumption, sorry, we have stated that potential energy is negligible. So this term must be considered as zero. So we just need to estimate the enthalpy and the kinetic energy of the fluid. So in this case, we have the information about the velocity of the flow of the fluid. Sorry. But we need to estimate. Remember, estimate the enthalpy. Remember that enthalpy depends on the properties of the fluid. Yeah, in this case, it depends on the properties of the air, specifically their its temperature or and its pressure. Yeah. So in the case of ideal gas, remember enthalpy is just function of the temperature. Yeah, yeah. The effect of pressure over enthalpy in ideal gas is negligible. So um, maybe, or I'm sure that you in your previous thermodynamics course have discussed this equation. Yeah, this is the equation for the enthalpy of an ideal gas depending on the heat capacities and temperature. Yeah, so in this case, we have stated that heat capacity is constant, and yeah, it means we usually, I'm getting back to the table. Yeah, here we have um, heat capacity, but heat capacity is measured at this temperature, 300 Kelvin. Yeah, this is quite near the standard temperature. Yeah, this is 27 Celsius degrees. So we have air at a high temperature. So in an strict sense, we need to re-estimate this heat capacity for this temperature. So, as we have supposed that heat capacity is constant, we can use this value for the heat capacity even though the temperature is not the same. Yeah. So in this case, we're going to consider that this heat capacity of 1.005 represents or can be taken as the heat capacity at the gas condition. Yeah. So in this case, we just need to substitute the values for all the quantities. I can use this formula to represent or to write the enthalpy in the energy equation, and we just need to substitute. We know the molar, the mass flow rate, the heat capacity. Remember, we need to consider or substitute the temperature as an absolute quantity, the velocity, and here we have an important fact. If you see the units of this quantity is kilojoules per kilogram. Yeah, this is a specific energy in kilojoules per kilogram. But in this case, the units of this is square meter per square second. So if you do an analysis at the level of fundamental units, you can see that this quantity equals to joules per kilogram. Yeah. So if you see here we have the same units, but in a different scale. Yeah. So we need to write this to write the both quantities in the same scale. So here I have included a conversion factor in order to write this quantity in kilojoules per kilogram. Yeah. So in this case, I have estimated uh, both factors, the specific enthalpy and the specific kinetic energy by separate in order to show the difference between these two values. Yeah, sorry. In this case, I have written, but let me correct. Both are right now in kilojoules per kilogram. Yeah. So if you see enthalpy is uh, higher than specific kinetic energy in a very high level. So in this case, we could assume that specific kinetic energy could be negligible too, as with the potential energy. Yeah. Finally, if we do the operation or we calculate the value, we get that the energy flow rate is um, 6,333 kilojoules per minute. Yeah. So, um, if you have any doubt about this exercise, please write back to me. Have a nice day.